So let's talk about how to measure volume by dilution in an unknown volume of water. So the first key is to know what is the conductivity, the electrical conductivity of that water before we add our tracer. In this case, tracer refers to our sodium chloride, our tracer solid that we're going to dissolve in the water. The reason we want to know that is because we don't really care what's causing the background conductivity, this 350 microsiemens per centimeter that we're measuring in the water before we've added any salt. We don't want to account for that by our change in concentration induced by the salt, or we're going to get an error in our answer because this conductivity meter could be coming from anything. It's not coming from the salt we're adding. So we have to do what's called background correction with our conductivity measurements to make sure we're just talking about an increase in conductivity due to an addition of a mass of salt to the bucket. So we're going to call our background conductivity, our EC background in our bucket, BBG, at 350 microsiemens per centimeter. Our conductivity measures that before we add our salt. Then we're going to add a known mass of salt to this bucket. In this case, it's going to be 1,000 milligrams or 1 gram of salt. I'm not sure you know exactly how to estimate what a gram is, but a gram is not a lot of mass. We're not talking about a lot of salt here. We're talking about 1 gram, 1,000 milligrams. So we add this known amount of salt and we stir up our bucket and make sure the salt completely dissolves. You know, none of this is going to work if some of the salt is not dissolved and not having the potential to affect the conductivity of the water. So before we measure our conductivity again, we have to make sure that salt is fully dissolved. Okay, so we've got our salt fully dissolved. We can put our conductivity meter back into the bucket, and now we have an increased conductivity that we're measuring due to the salt that we added of 475 microsiemens per centimeter. So we will call that the electrical conductivity of the bucket with the salt added, and that will be 475 microsiemens per centimeter. Now what we're really interested in here is how much that mass of salt has changed the conductivity. Because if we can figure out from the change in conductivity, the change in concentration, then we should be able to do some relatively simple algebra to figure out the volume of water that must have been in that bucket before we added the mass. So our change in electrical conductivity was 125 microsiemens per centimeter. I just subtracted 350 from 475. And remember, we know this relationship that a 2 microsiemen per centimeter change is dimensionally equivalent to a 1 milligram per liter change in concentration. So we can set this up very similar to a unit conversion, where we can take the change in electrical conductivity and come up with a change in concentration with a simple unit conversion type calculation. So we want to have that 2 microsiemens per centimeter in the denominator, so it will cancel and get rid of microsiemens per centimeter and leave us with milligrams per liter. We know that there are 2 microsiemens per centimeter for every 1 milligram per liter change, so we can set up our factor that way. And that gives us a change in concentration that is similar to our change in EC, if we think of EC as a concentration measurement as well, 62.5 milligrams per liter. So we know from 125 microsiemen per centimeter change in EC that we have a 62.5 milligram per liter change in concentration, and we can use the unit factor approach to help us make sense of that math. So now we have everything that we need to know in this equation except for the volume. We know what the change in concentration was, the change in C and NaCl. We know what the mass was that we added, so we can just rearrange this equation for concentration to give us the volume of the solution. Once we have that equation rearranged, we can plug in the numbers. We've got 1,000 milligrams for the mass of NaCl that we added. We have a change in concentration of 62.5 milligrams per liter. We know that this is going to give us a volume because we can work through the units through our calculations. We've got the units on those numbers. We see that the mass is going to divide out The per liter is in the denominator, so when we divide by that number, the result is going to be in units of liters. So 1,000 over 62.5 is about 16. So the original volume of water in that bucket was about 16 liters. So this is a pretty absurd way to come up with the volume of water in a bucket, but is exactly what we do when we do dilution gauging. It's the exact same idea where we take a known mass of salt, we throw it in the stream, we measure electrical conductivity somewhere downstream. The math just gets a little bit more complicated because you have to account for the fact that the volume of water that you added the salt to is moving past you in a stream. And that adds some more math that we'll talk about later. So this is an odd way to measure a volume in a bucket, but it gives you the basic idea of how dilution gauging works. So we've got 16 liters in our bucket. There are a couple of assumptions that we have made here that we really should pay attention to make sure that we're not making any mistakes. First of all, we're assuming our salt is what's called a conservative tracer, chemically conservative. That means when the salt, the mass of salt dissolves in the water, that none of that sodium chloride reacts with anything else to change the concentration in such a way that that 2 microsiemens per centimeter per 1 milligram per liter change is inconsistent. So you have to have a conservative tracer to do this type of work, hydrologically speaking. Also, we're assuming that the solution volume is equal to the original water volume. Remember that in this calculation, this volume that we're calculating is the volume of the solution, not the volume of the solute. So the fact that our original volume might change if we add a mass to it is something that could cause error in this estimate. Now, when you talk about 1 gram of salt, that's a very small volume of salt. So even if it does change the volume of water in the bucket a little bit, it's probably not going to change it within the amount of error that we have due to our ability to measure electrical conductivity or our faith in that relationship in the 2 microsiemens per centimeter change with 1 milligram per liter of concentration change. So in this case, this is a very small amount of salt relative to the amount of water in the bucket, and the fact that sodium chloride has such a strong effect on conductivity would make this estimate pretty robust. So these are a couple of, but these are 2 assumptions that you need to be able to make when you're applying this method, and that's true for dilution gauging as well.